Hey, this next section, 9.3, we're going to start off talking about the integral test. So integral test, we can use, this is a next test that's available to us to help us determine whether an infinite series converges or diverges. There are a couple of restrictions here with the integral test. So first, the function needs to be positive, continuous, and decreasing for x greater than or equal to 1. So an example of this is this graph where it is positive because it is above the x-axis. It is continuous with there no breaks in the graph after x is for values to the right of 1. And also, this graph is decreasing. So it needs all these characteristics in order for us to continue, in order for the conditions to be met. Okay. And if that's the case, then the sum of the series and the integral of that f of x, or letting f of x being the same as the rule the a sub n, the rule of sequence. Then if we can find the integral of this, or find the value of this improper integral, if the result of this improper integral converges, then we know that the sum also converges. However, if the result of this improper integral diverges, then we know that the series will also diverge as well. So, however, a couple of notes here. This does not mean that the series converges to the value of the definite integral. So whatever the result of this is, it does not correspond to the actual value that this series will converge to. Okay, it's not as clean as the geometric series, where we can determine that the series converge and figure out the sum that it converges to. In this case, this test is only good to determine whether this series will converge or diverge. Second, the function need only to be decreasing for all x greater than k for some k greater than or equal to 1. So we're looking at the long-term behavior. It doesn't have to be decreasing for all of x greater than k, just for some k greater than or equal to 1. So dependent on the problem. Okay, let's look at some examples here. We're going to look at this series, the summation of n over n squared plus 1. Now this says apply the integral test, but we're going to go through our list of tests in order. So the first thing that we always do is we always do the nth term test for divergence. And if you look at this, we find the limit of this rule of sequence. We see that this denominator, it will be growing at a faster rate than the numerator. And so this, the limit as n approaches infinity will be equal to 0. And if it's equal to 0, then that tells us that the nth term test is inconclusive. We can't simply say that this is divergent because this nth term test is inconclusive, but we still want to go through and let that be the first thing that we always look for. Okay, this is obviously not geometric. It's not telescoping series either. We can't break this down using by splitting this up into individual fractions. So not telescoping and not geometric. And so we go and see if this function, it is positive, okay, for n squared than 1. This function is decreasing. This n squared plus 1 is growing faster than n. And then also this continuous. Okay, there's no breaks in the graph. So let's see if we can test this using the integral test. So integral test of x over x squared plus 1 as 1 from 1 to infinity. We can find, go through u substitution, let the u value be x squared plus 1, du over dx is 2x. dx is du over 2x. We make our substitutions, and the dx gets replaced with du over 2x, which cancels out with the x. We have to pull the 1/2 out as a coefficient, and the integral of 1 over u is simply natural log of u, which becomes natural log of x squared plus 1. So we find the limit as b approaches infinity, and we evaluate between our upper and lower bounds being b and 1. So we plug b in for x, and we get natural log of b squared plus 1 minus 1/2 natural log of 2. and then the b squared plus 1 will eventually go to infinity. And so this improper integral will result in a divergent value, positive infinity. And since the integral of this rule of sequence goes to infinity, diverges, then we can say that the sum will also diverge due to the integral test. Okay. Example 2, the summation of 1 over n squared plus 1. Again, we want to decide, we see that this will will pass the conditions positive. For all n greater than 1, this expression will always be positive. Continuous, no breaks in the graph. Decreasing, because the denominator is greater than 0. And technically, we should have gone through the nth term test for divergence. So we see the nth term test for divergence will be inconclusive because the limit as n approaches infinity for this expression will go to 0. Okay. Again, not geometric, not telescoping. So we can look to see if the integral test will work. So we find the integral from 1 to b as as b approaches infinity. And we can't go through u substitution, but this is a rule where we can apply the arctangent. So arctangent is u prime, or in the form of u squared plus 1, or plus a squared. And arctangent of x over 1 is the integral of 1 over x squared plus 1. And we evaluate between upper and lower bound, arctangent of b. So arctangent of infinity will be pi over 2, because that's where the vertical asymptote is. Arctangent of 1 is pi over 4. So pi over 2 minus pi over 4, this is a finite value. So because the integral of this rule of sequence goes to a finite value, so therefore it converges. And so because this converges, we know that the sum of the series will also converge as well by the integral test. Note, however, that this value does not represent the sum of the series. Again, this only tells us that the sum will converge, but because this is a finite value, however, this does not mean that the series will converge to this specific value.